Okay. Okay, so thank you again for joining today's session to all of you. So welcome back to the fifth live interactive session for the NPTEL course Applied Linear Algebra for Signal Processing, Data Analytics and Machine Learning. This course is offered by Professor Aditya Jagannatham from IIT Kanpur. Now, a little bit about myself. So, my name is Yashvanth, and I'm presently a PMRF Ph.D. research scholar at the Department of EC at Indian Institute of Science, Bangalore. My current research advisor is Professor Chandra Murthy from EC at IISc, and my research interest broadly lies in statistical signal processing and wireless communications. I currently focus on working on designing algorithms and analyzing the performance of systems with intelligent reflecting surfaces for 5G and beyond wireless communications. To contact me, you can always write to me at this email ID, yashwanth.l@iisc.ac.in, and you can find more about me in this particular website. Okay, so with that very short introduction about myself, the topics that we will be looking for today will be on the properties of eigenvalues and eigenvectors, and then jumping into the least squares and applications, which was the focus of the lectures for this week. So as usual, what we do is we are going to now jump into the summary of week 5's lectures. Okay, so the week 5 was broadly on least squares based techniques. Okay, so to motivate what least square is, I'm going to again go back to the system of linear equations, which we in our one of the earlier sessions we saw on different scenarios. So a system of linear equations can be described by this equation ax equal to b. Okay, so here the x vector basically has all the unknown variables, and b vector is the observations, and a is the coefficient matrix that collects the linear coefficients of the variables. For example, this is nothing. If I have 5x1 plus 4x2 equal to 3 and 2x1 minus 5x2 equal to 1, so 3 and 1 will go into the b vector. 5, 4, 2 and 5, these four numbers will go into the matrix A, and the x vector will just be x1 and x2, which is the vector that we want to find. Okay, so given ax equal to b, the idea is to find the vector x such that ax equal to b. Now the solution to the vector x, it exists if the vector b lies in the column space of the matrix A. That is, the span of all the column vectors. That is, if A is equal to, let's say, A1, A2 and so on till AN. Okay, maybe just a minute. Okay, I can't reduce the thickness, no problem. So if A equal to A1, A2 and so on till AN, then what is column space of A? It's just the span of all the vectors A1 to AN. That is, you span the subspace spanned by these vectors, the column vectors of A. Okay, so the space spanned by these column vectors of the matrix A is called as a column space of A. Okay, now the solution to Ax equal to B will exist if the vector B lies in the column space of A. What does it mean? If you can express the vector B as a linear combination of, C1, A1, linear combination of these column vectors plus Cn, An. If I can express this B vector as a linear combination of all these n vectors with corresponding coefficients C1, C2 and so on to Cn, then you can find a solution x. In fact, the C1, C2 which I described in the equation itself is a solution which is x, x1, x2, right? x1 equal to C1, x2 equal to C2 and so on till xn equal to Cn. Correct? So the solution to x exists if D lies in the column space of matrix A. But if the solution will not exist if the vector B does not lie in the column space of A, right? So you cannot find any x such that Ax equal to B will be satisfied. Okay, so in this regard, we saw what is a consistent equation system of equation. If a solution exists, then the system of linear equation Ax equal to B is said to be consistent. That is, there is a solution. Okay, in that case, we saw two categories, namely that of unique solution and another is infinitely many solutions. Under the category of unique solution, we saw when will unique solution exist? If the rank of the matrix A is same as the rank of the matrix A augmented with the vector B. Okay, if I compute the rank of this augmented matrix and the rank of the matrix A, both of them have to be equal, and both of them are equal to the number of columns of the matrix A. If this condition is satisfied, this system is a consistent system with a unique solution. That is, there can only exist one x such that Ax equal to B is satisfied. Whereas if we saw that if rank of A equal to rank of A augmented with B, this is a condition for consistency. That is, you need a solution. And if this number is less than the number of columns in A, then the system Ax equal to B is consistent. That is, it has solution, but it doesn't have just one solution. It has infinitely many solutions. Okay, so these are the two possibilities for a consistent system of linear equations. Okay, that was this we saw in elaborate in one of the previous sessions how to compute how to first check whether there's a unique solution or not, how to compute the unique solution, and similarly how to check whether the system has infinitely many solutions or not, and how to compute those infinitely many solutions. We saw them in detail in one of the previous TA sessions. Now, if the solution doesn't exist, that is, if you cannot find any vector x such that b is equal to ax is satisfied, if you cannot find such kind of vector x, then what is the best we can do? Then the best approximate solution that minimizes this error. You see, I want to find x such that b is equal to x, but now I know that I cannot find such an x. Why? Because b does not lie in the column space of A. If this happens, then I cannot find a solution. Right? If I cannot find a solution, what is the best I can do? I can find such x such that the error, that is b minus ax, it's a vector. See, b is a vector, ax is a vector. The subtraction is given error vector e. It's a vector. I want this vector e to be as minimal as possible. Okay. In other words, to measure the the minimality of this vector, I take the norm of the vector. Okay. So then what we do is, if solution doesn't exist for b equal to x, then we want to look for the best approximate solution that minimizes the norm b minus ax. For mathematical convenience, we take a square also. Okay, so b minus ax is the error vector, and take the norm is same as the error of the norm of the error vector, norm square to be precise. So we want to find such an x such that the norm is minimized. Now, if you in the class, professor would have expanded this in terms of inner product, because E norm square is same as E transpose E. This is same as B minus AX transpose times B minus AX. And then he would have expanded it. And for minimization, you need to take the gradient with respect to the vector X, which we want to find, and equate to 0, and you get the value for X, right? That's how professor proceeded. And the end result is this. Xi is equal to A transpose A the whole inverse A transpose B. Okay, this is also called the least square solution. Why is it called least square? It's called square because I'm minimizing the square of something. This is a number. B minus AX L to norm is a number. I'm taking square of that. So that's why the term square comes. Why is it least squares? Because I want to find the square of the least number. Okay, because I want to b minus ax, if I minimize, what does it mean? I'm trying to find the least value that this particular number can take, and I'm taking the square of the least number. That's why this is called the least square solution. The least square solution x is given by this particular matrix A transpose A the whole inverse A transpose B. Okay, now what is to be understood from this equation? See, I'm defining something called A transpose A the whole inverse. What does it mean? This solution the x hat, this is called hat. If I put say x and make a this kind of a symbol on top, it's called hat, HAT. Okay, now this solution is valid only if the matrix A transpose A is full rank. Why? Because I'm taking the inverse of this matrix. Who told that the inverse exists, right? So this A transpose A must be full rank matrix so that it is invertible. Now, let's say A is any matrix. Let's say A belongs to C to the m by n. Okay, it's an m by n matrix. What is the? Can anyone tell me if A is m by n? What is the dimension of A transpose A? Can anyone tell me? A is a m by n matrix. Then what is A transpose A is what?
N by n.
Correct. N by n. Okay. Now, so that means what does it mean? This matrix A transpose A should be full rank. It's a square matrix. Now, remember that's why I'm able to compute the inverse. The square matrix. So n by n matrix. If it has to be full rank, what does it mean? It should be the rank should be equal to n itself. Only if the that is what is n? The number of columns. The matrix A. Okay, the number of columns in the matrix A. That's why suppose if I can show that the matrix A, the original matrix A is full column rank, that is the rank of A is equal to n, then there is a fact that says that, there's a fact that says that rank of any matrix A is equal to rank of A transpose A. It's a fact. Today we will solve this problem. A very, very important fact. Rank of any matrix A is equal to rank of A transpose A. Okay. Now, A transpose A is nothing but it's an n by n matrix. If I want this to be full rank, then rank of A transpose A should be n only. But I know that rank of A transpose A is same as rank of A. That means if I say it's a rank of A equal to n, that means what does it mean? But n is the number of columns in the matrix A. What does it mean? The matrix A should be full column rank. Namely that all the columns of the matrix A should be linearly independent. Only then this solution is valid solution. Otherwise, this solution is not a valid solution. Okay, we will today. So what is left to prove is rank of A equal to rank of A transpose A. What is the proof? How to show this? Today we will. That is one of the problems that we will solve. Okay, that's why this solution is valid only if A is full column rank. Namely that the rank of the matrix A is equal to the number of columns in the matrix A. Okay. Now, in another class, professor would have explained what is least square as from a geometric view. That is, least square solution is obtained by projecting the vector B onto the column space of the matrix A. Okay. So let's say the projected vector B onto the column space of matrix A be B proj. Okay. Let's call this projected vector. That is, if I have a vector B and let's say there's a column space of C of A, I project this onto the column space of A. Call this vector as B proj. Okay, the projected vector is B proj. Then essentially what least square does is it will, instead of solving for Ax equal to B, it solves Ax equal to B proj. Now you see B proj by definition it is already projected on the column space of A. That means it definitely belongs to C of A. That means this system of equation Ax equal to B proj has a solution. Has a solution definitely. It cannot have a solution. It's not possible for it to not to have a solution. It always has a solution. Solution exists always. Why? Because B proj by definition it always lies in the column space of A, and the resultant X that you get is called the least square solution. Okay. This is other interpretation that professor had done in the class. Now, the next, in one of the other sessions, professor had mentioned the application of least squares in wireless communications. Namely, he considered a zero forcing receiver. Okay, so what's a zero forcing receiver? Let's consider that there is a transmitter which wants to send some information to another receiver which is separated in space, some very distant. Let's say there is a tower, and we all of us have mobile phones in our hand, and we are separated from the tower. So the channel between, let's say, the tower and our user equipment, right? Our mobile phone, or maybe I will say this as mobile phone. This mobile phone, for example, and let's say this is base station, or it's called base station in more precise terminologies, or let me call this tower. Okay, there's an underlying air channel in between. Let's say the base station or the tower has NT antennas, and let's say our mobile phone has NR antennas. Then I can write down the receive equation at the mobile phone as this particular equation. Okay, y equal to hx plus w. Y is basically an nr cross 1 vector. That is, the data I received in first antenna is y1, data on second antenna is y2, and so on till data on the nrth antenna is ynr. I stack all of these information into a vector and call that as y vector. Okay, this is also called the received symbol vector at the mobile phone, because here I'm considering the receiver to be a mobile phone. Okay, H is the channel matrix. That is, for example, what is the channel between the first antenna of the tower and the first antenna of user? This is called H11. This channel between the last antenna of the tower and the last antenna of receiver is called HNRNT. The first index represents the antenna number, antenna count of the receive antenna, and the second index represents the antenna count and the transmit antenna. Okay, so if you collect, so there are NT antennas here, there are NR antennas here. So total number of channels, if you see, you'll get NRNT number of total channels. If you stack all of them into a matrix, you get the matrix H, which is a NR cross NT matrix. And the symbol, the data symbol that is transmitted from the tower, let us call it as the vector X, which is an NT cross 1 vector. And in any communication system, it's inevitable to avoid noise. So I add some noise into the received symbol. It's not always possible that whatever you send from the transmitter will come into the receiver. You will always have some external noise due to the environment. That I model as the W. Call it as NR cross 1. Okay, so now see, it's NR cross NT cross 1. So total is NR cross 1. This is NR cross 1. This is also NR cross 1. So all are NR cross 1 vectors. Now, once I receive Y, so at the mobile phone receives Y. Now, what is the objective? The mobile phone now wants to know what is the data that the tower wants me to understand. That is, given Y, the mobile phone has to estimate what X is. Okay. Then what should I do? I cannot do anything about the noise, because noise is something that the mobile phone is ignorant of. It's agnostic of. Okay. But what I have in my control is the matrix H. H, you can always, through some means, the mobile phone can first find what H is, and then maybe do something like H inverse on both sides, so that you can nullify the effect of the H. Then whatever the output you get at the end of the receiver processing will be the estimate of X hat. It will be the estimate X. So now the goal is to design a receiver such that we recover the transmit symbol vector X, such that I impose an additional constraint, which will become more clear in one of the other problems that I'll solve today, such that the interstream interference is minimized. Okay, for now, don't worry about what this means. This I will be doing in elaborate today. Professor would have told you that it can cancel inter-user interference, right, in one of his lectures. I will I will show today what does it mean. I will explain all these things in detail. But for a moment, if I want to design a receiver detect or decode what my transmitted symbol X was, then you need to do, the answer is something called a zero forcing receiver. Okay, essentially is a least square. See, what is this? H inverse H the whole inverse H inverse. This is also called the pseudo inverse of H. Pseudo inverse of H if H is full column rank. Because if H is not full column rank, this matrix is not defined. You cannot find inverse first, so this is not valid. If H is full column rank, the pseudo inverse of that matrix is given by H inverse H the whole inverse H inverse. H Hermitian H the whole inverse H Hermitian. Or if all the matrices are real matrices, then it's called H transpose H the whole inverse H transpose, whatever it is. Okay. Then the detector is just a least square. What is this? I'm just giving hx, sorry, yeah, y is equal to hx plus w. Since I know I have no control over w, what I will do is find x. such that y minus hx norm is minimized. That is the problem. Is sorry, I'll write it here. Find x such that y minus hx norm is minimized. This is precisely the least square estimate of x, right? And that's what I've written here. So this is like the role played by b, and this is like the role played by a, and this is x itself. So b equal to x. So b here is y, a here is h matrix, the channel matrix. So h is also called the channel matrix. Okay. So then this particular matrix, H inverse H Hermitian H the whole inverse H Hermitian, is called the pseudo inverse of H. That is, it's a proxy because H is not invertible. Can anyone tell why H is not invertible?
Rectangular.
Correct. One rare reason is it's a rectangular matrix. Inverse doesn't exist for rectangular matrix. That itself is sufficient to tell that inverse does not exist. So proxy, for the inverse is given by, it's called pseudo inverse. That's why it's called pseudo inverse. Now you see this matrix is called a pseudo inverse. Why? Because if you see, why is it called pseudo inverse? Let me explain here. Okay, let's say, what is it? Let's go back to the definition of, okay. Maybe I'll do it as a part of first question. Then we'll go back to the summary. For a matrix A, which is full column rank, Y is A Hermitian A the whole inverse A Hermitian called the pseudo inverse. Okay, now here is the solution. Okay, now what is the property of inverse? If A were invertible, that is, it's a square matrix and it's a full rank square matrix, then A is an invertible matrix. Okay, then what does it mean? A inverse A is equal to, what is A inverse A?
Identity.
Yes, correct. Identity matrix. So what is precisely the inverse? Inverse means what? If I post multiply, let's say B is equal to A inverse. Okay, that means if I post multiply the inverse of the matrix, inverse of A, that is B, by A, that is, if I post multiply B by A, it should result in identity matrix. Correct? B times A is equal to I, where where I have defined B is equal to A inverse. Similarly, if I call B is equal to A Hermitian A the whole inverse A Hermitian, can anyone tell me what is B times A?
I.
Exactly. It's equal to I. So somehow, see, I found a matrix A, I found a matrix B such that BA equal to I. Correct? So basically, I have achieved the goal of what an inverse should do. Okay. That's why this particular term is called pseudo inverse. It's called pseudo inverse. Because BA equal to identity, which is what, the defining characteristic of any inverse matrix. And now can anyone try to guess why then this is not the inverse itself? Why am I calling pseudo inverse?
Because inverse is for the square matrix. No?
Sorry?
Inverse is defined for square matrix only.
Okay. That is correct. Okay, that is one way to argue. The other very important aspect of what is invertibility is, if BA equal to I, it is not just, A inverse A is equal to I. The other way should also hold true. A inverse should also be equal to identity matrix. That is also the defining characteristic of an invertible matrix, inverse. But if you now compute AB, what is AB? A into A Hermitian, A the whole inverse, A Hermitian. What is the guarantee that this is an identity matrix? There is no guarantee. It's not identity matrix. The one way relation holds true, but the other way relation does not hold true. Okay, that's why it's called pseudo inverse. It's some kind of an it tells something about the invertibility, but it is not the inverse of the matrix at all. Maybe at a very high level you can think of like this, that it's a rectangular matrix, so you cannot define the inverse. That's a very high level argument, agreed, but this is more general. Okay, in fact,
but sir, excuse me, but pseudo inverse
sorry,
different
I'm not able to hear you properly.
pseudo
for tall and wide matrix.
Correct. See, that's why if you see my question, I carefully mentioned for a full column rank. If it were not full column rank, first of all, I cannot even compute this matrix. Okay, what is full column rank? Means all the columns should be linearly independent. Okay, that means we know that for any matrix, row rank equal to column rank. And if I want it to be full column rank, what does it mean? The number of rows should not be less than number of columns. Only then can the full column rank condition be achieved. Now, for that to happen, what does it mean? The number of rows must be at least the number of columns. That is what I'm trying to say is, number of rows should be greater or equal to number of columns. Only then full column rank can be achieved. Okay, what does this mean? It's a tall matrix. This is more, but this is less. This is less. It's a tall matrix. So this particular definition, this particular computation is only valid for a tall matrix. Okay. Anyways, that's a side point. But what I'm trying to say is this is only a pseudo inverse. In fact, to be more precise, this is also called the left inverse. Because only if I multiply the matrix A from the left side with some B, I get identity. I don't get the right multiplication from A, I don't get identity. In fact, the pseudo inverse that we are referring to in the least square is in fact to be more rigorously called as the left inverse of the matrix A. But anyways, for the purpose of this course, consider that your matrix A is always full column rank. Namely that we only consider tall matrices. That is, the number of rows is more than number of columns. In that case, it's always a left inverse or left inverse that we consider as a pseudo inverse. Okay, I hope now this is clear. Pseudo because only one side multiplication will give identity, the other side multiplication will not give identity. Okay, now let's go back to our system of our pseudo inverse. So this is there was a short digression that we had on pseudo inverse. So essentially the solution x hat is nothing but we are just trying to find x, the argument x that minimizes this quantity, the L2 norm of y minus hx square, which is the least square. That's why one of the application of least square is in designing a zero forcing detector or zero forcing receiver. The next application which professor had done in the lecture was on channel estimation in multi-antenna communication system. Okay, so channel estimation. What is channel estimation means? Essentially, I want to estimate all the entries H1 and so on till HNT. Note, if you see the previous this particular question, I don't know what X is. I know what Y is. I assume that I know what H is. And then I find this estimate of the transmit X as this particular matrix. Now see, this can be computed only if you know H and if you know Y. So this is called the data decoding, or you want to detect what the data is from the tower at the mobile phone. Now in another, I know the counterpart problem is, okay, now how to find the matrix H itself? Okay, then what we do is, that problem is called channel estimation. What is the channel? Okay, so for an example, if you consider NT number of antennas at the transmitter and a single antenna mobile phone, okay, then what is the channel? It's just a vector h1, h2, and so on till hnt. If you stack as a vector, it's just one vector of nt cross 1. Unlike a matrix here, ANR cross nt, because both the sides have multiple antennas. Here, only one side has multiple antennas, other side has only one antenna. Now, the goal of this problem is to find h1, h2, and so on till hnt. This problem is called channel estimation. Now, in order to do this problem of channel estimation, what we typically do is we do something called pilot transmission. That is, in this problem, the previous problem, the receiver did not know what x is. That's why it's doing the estimation of x. Correct? But if the receiver knows, the receiver anyways know y, because that is what it receives from the air. If in addition, if the receiver also knows what x is, that is the data that the transmitter transmits, then it is like, for a moment you ignore noise. Okay, for a moment you ignore noise. It is like y is equal to ax. You know what x is, you know what y is also. The only variable that is remaining to be solved is the matrix A itself. And that is what is called the channel estimation, the matrix estimation, right? So basically what here you assume is, you know what x is and you know what y is, because that's what you receive. You want to find what h is. That is channel estimation. But in the previous problem, you know what h is, you know what y is, and you want to find what x is. That is called data detection. So if you see any communication literature, you will find these two terminologies very often: channel estimation and data detection. Channel estimation, data detection. Data detection. They are two independent problems, but sometimes they are coupled. Sometimes there's also something called joint data detection and channel estimation. There are a lot of research works on these areas, but I have just explained you what the problem is. There are a lot of solutions, profound solutions that researchers have worked out on this problem. So now, if I want do pilot transmission, that is the symbols which are known at both transmitter and receiver. The receiver already knows what the transmitter is going to send. So these are symbols that's why they are called pilot symbols. These are called pilot symbols. So now, if you see at this, it's a single antenna receiver. So I can write y is equal to summation of hi xi, where summation is taken over all the antenna indices, and some noise, which is a 1 by 1 scalar, because it's just one. So it's a scalar equation. Okay. Now this is what this, you can write this as an inner product of the two vectors x and h, where h is basically collection of all the entries of h, and similarly x is equal to x1 and so on to xnt. Okay, if you define h and x like this is the inner product. Okay, h transpose x plus n is equal to y. Now what you do L such transmissions. That is, okay, basically I in x1, x2, and so on till xnt, all of them you transmit at the same time, I will get y1. Similarly, now choose a different set of x1, x2, and so on till xnt, do the transmission, I will then get y2. Like that, do L such transmissions. Then what you do is you collect all these L transmissions. You see y1 is equal to x1 transpose h plus n1. That is, x1 transpose means what is the transmitted vector at the first symbol. Here the I'm sorry. Here the subscript denotes the time, the which transmission index it is. The first transmission is y1 is equal to x1 transpose h plus n1. But note that h is independent of what we transmit. It's a channel characteristic. So h will remain the same in all the equations. But noise can potentially vary, because noise is something random. It varies with time. Okay. So if I collect all these L transmissions, I stack it now. Now you see I got L such scalars, stack it as a vector y. Now I have L such transmitted vectors. There are L vectors. Okay. So I can form the matrix X like this. Okay. Collect all the L vectors and form the matrix X. H is same as one small vector. Now again, you can collect all the noise terms as the n vector. you can show that you can rewrite all these L equations in this form. Y is equal to X transpose H plus N, where the matrix X is given by this particular concatenation. Now, what is this? How to now H is the thing that we need to solve for, right? What is it? Just take the least square, that is X. Now, X transpose is like your A matrix. So, Y is equal to AX, right? Where X is like your H and Y is same as Y. But you have noise term. That's why you go for the least square solution. You don't know what noise is. So I just want to do Y minus X transpose H. This error should be as minimum as possible. Then H is given by X transpose pseudo Y. Okay. So again, D square estimation comes into picture. Okay, maybe I will give a small engineering insight here. Now, for X transpose pseudo, so this part, if I say plus mark or something like that on top, that indicates a pseudo inverse, not a proper inverse. Proper inverse means I've written -1, but now I will just write something like a plus. Okay, to exist. What should be the condition? Can anyone tell? I told what is the condition that X transpose should satisfy? X transpose should be full column rank. Correct? Is it correct or not?
Yes, yes.
Now,
Yes.
so now you see what is the dimension of this X here? Can anyone tell me? It's a C
1 by
of
L.
no, it's
N by L.
NT cross L, right?
Yes, yes.
Yeah. So what is X transpose is? L cross NT. Is that right? Okay. Now, if it has to be full column rank, what is the relation between L and NT such that X transpose is full column rank? Necessary condition is what? L should be at least NT, right? It should be a fat matrix. Only then you can define this particular pseudo inverse here. Should be full column rank. Means what? The number of rows should at least be the number of columns. What does it mean? It means the number of pilot transmissions should be at least the number of antennas in the system. It's a very, very important. It's an engineering insight. It's nothing to do with math. It's engineering insight. What does it tell? It says the number of the number L should be at least the number of antennas. It's intuitive also mathematically. Why? See, each of the L transmission gives me an observation. So there are L equations. See, what is the number of unknowns in this picture? NT unknowns, because there are NT antennas, there are NT channels. So the number of unknowns is NT. And in order to solve an NT a system with NT unknowns, I need at least NT equations. Correct? That's what this particular insight is saying. I need at least those many pilot transmission, as many number of antennas are there in the system. Okay, this is what this particular math, this intuition is. Okay, yeah. So if you have any doubts, ask me here. Else we'll move on to the last part of this week's lecture, namely that application of least squares in machine learning. Okay, the first this is the first topic that, okay, there was another topic we introduced, namely PCA, in the previous classes, but there's another topic called linear regression. Okay, what is the problem in linear regression? Okay. So given a set of data points and a noisy observation of these data points, okay, we know that there are some data points, but we don't know what these data points actually are, but we get to observe a noisy observation of these data points. Then the goal is to fit a curve. Okay, the goal is to just fit a curve, determine the functional relation. Maybe let me an example. Let me illustrate. Suppose the actual function is f of x is equal to x square. Okay, all are scalar numbers. Let's say real numbers for a moment. F of x equal to x square. But I really don't know that this is the function I'm talking about. The functional relation that f of x equal to x square is something unknown to me. I don't know. But instead, what I do is I get to observe for every input value xi, I get to observe yi is equal to f of xi plus ni. Consider it to be like a system. Okay, there's some kind of a system. Okay, that implements if x is the input, that the output is equal to f of x plus n. Where n is some noise. We don't know what that noise is. Okay, but I don't know what the f of x is, but I know that the system applies some f of x. I don't know what that f of x is. The goal is to find what f of x the system applies. Okay, for example, if f of x is equal to x square is a true function, then I need to somehow find that the system is applying a square to the input. I need to find that. That is the goal of the regression. That is, I need to find a fit between the input and output, some curve that can approximate the input-output relationship of a given system. Okay, but in general, I only get to observe a noisy system, because any engineering application, you cannot avoid noise. You need to model the input-output relation as a noisy observation for any engineering application. Okay, so for example, curve fitting. So we know that actual y is equal to x square will be something like this. If I say the positive quadrant, it will be something like this. This is my y is equal to x squared. This is x and y. But what I will do, I will not get this. I will get some, points which are cluttered around the point. These different violet points you see here, or each point is an observation. Xi comma, it's not f of xi. If it's f of xi, it would have strictly lied on the curve y is equal to x square. But it's perturbed by a noise ni that varies with the observation index. For every I, ni will keep changing. That's why there is some kind of a oscillation. All these violet points are scattered around the main curve. But in general, I get to observe all these different points. Now, from the given points, I need to find the approximate curve that these points fit into. That's called curve fitting or linear regression. Okay. Okay. One of the very famous regression is called the polynomial regression. Okay. What I do is I model any function f of x to be an nth degree polynomial. Sorry, or n minus 1th degree polynomial or nth degree polynomial. The general equation of any n minus 1th degree polynomial is given by this: w naught plus w1x and so on till wn minus 1 times x power n minus 1. Okay. Now what I do is I collect all the observations. I collect xi comma yi. Xi comma yi. That is what input I give and what output I give at the ith time instant or ith observation index. So y1 is equal to w naught. So see, what is the characteristic of this function? If I tell you what w naught, w1 and so on till wn minus 1 are, if I tell you what these coefficients are, I have precisely characterized what this f of x is. If I say f of x is equal to 2x square, all I need to know is what is this number. If I know it's 2, and if I know the degree, the power of these numbers, okay, then I have told you what the function is. Now here what I'm saying is I'm saying that it will have all the powers from 0. This is 0th power of x. This is the first power of x. This is the second power of x, and so on till n minus 1th power of x. All I need to tell you is what these wi's are: w naught, w1 and so on, wn minus 1. If I tell you, if I somehow find these values, I know what the function is. Correct? That is the goal that I'm going to. What if for this, what I'll do is I'll collect some L observations again as like pilot. Y1 is equal to W naught plus W1x1 plus W2x1 square and so on till Wn minus 1 x1 power n minus 1 plus n1. That is a noise at the first observation index. Take the second observation from a second input. Give some other input x2. You're only exciting the system, right? So you know what these inputs are. And for the given inputs, you're observing what the output y's are. And for these given pair, tuple, x and y, you're trying to compute what these w's are. That is the problem of regression. Okay. And you collect L such observations. So you get L equations. And how many unknowns are there in the system of linear equations? Yes. How many unknowns are there in this? No. I'm saying how many unknowns.
Unknown are
wn minus 1.
Correct. All these W's are unknown to me. So how many such
Total N.
W's are there? N. Correct. So it's basically
N,
a
yeah.
system of L equations in N unknowns. Okay. So I can write all these, input-output relationship equations as, kind of a matrix vector relation. Basically, if you multiply the first row with this 1 times W naught plus x1 times W1 and so on till x1 power n minus 1 times Wn minus 1 plus n1 will give y1. That is what my first equation is. Okay, so I have just written all these L equations in the form of a matrix vector product relationship. So this is an L by 1 vector. It's called the observation vector. This is a matrix of size L cross N. It's called the known input matrix because it comprises of all the inputs that we give to the system and we know it in prior. And this W is a N by 1 vector. It's an unknown weight vector which we have to estimate. And the N vector is a L cross 1 vector, which is a noise, which we do not know under any circumstance. Then how to find W? Again, go back. This is the equation. Y is equal to xW plus N. What is the best W? Go for least square. X transpose X the whole inverse X transpose Y, where X is given by this matrix. You know how to construct X because you are the one who give the input to the system. And Y is also known because you get to observe what these Y's are. Once you know X matrix and Y, just go ahead and compute the vector W. Okay. So once you know what W hat is, what is the best curve that fits the given data points? You remember that W hat is a vector. What is the entries? W1 hat, W naught hat, W1 hat, and so on till W hat n minus 1. Okay. So then the best fit is given by this particular equation. This is the best function that approximates the input-output relationship of the given L data points. Okay. All right. So are there any questions here? Okay, great. Then
So
let's.
what is that matrix, sir?
Which matrix? Sorry.
This is tall matrix you discussed. Now, fat matrix also has pseudo inverse.
Yes, that's a very good question. For fat matrix, you define something called the right inverse. Okay. So it's for fat matrices, you don't have left inverse. They have something called the right inverse, and you can Google about it and check. Okay. In fact, pseudo inverse this is not the pseudo inverse definition as such. If you see pseudo inverse definitions are something different, but it's so where is the pseudo inverse? It so happens that if for a matrix it is full column rank, the definition, if you work out the definition, if you work out the pseudo inverse, it turns out to be this particular matrix H Hermitian H the whole inverse H Hermitian. Okay, pseudo inverse means this is not a pseudo inverse. Pseudo inverse is some other definition. Okay, for a matrix with full column rank, this particular matrix will turn out to be the full pseudo inverse. So similarly, for a full row rank, which is like a fat matrix, which you're saying, there is different kind of pseudo inverse. Okay, the Hermitian will now change. It will be something like H Hermitian the whole inverse. This is something different. This is not same as this. Okay, you can check about it. You can check online about left inverse, right inverse. I think very classical text for these things is the introductory linear algebra book by Gilbert Strang. He has very well explains what is left inverse, what is right inverse, and when will they be same. So if A be equal to I and if B is said to be the right inverse of A, if BA equal to I, then B is said to be the left inverse of A because it's coming in the left. But if AB equal to BA equal to I, that means B is said to be the proper inverse. It is the inverse of the matrix A. So if any invertible matrix, the inverse is same as the left inverse, which is same as the right inverse. Okay. And this left inverse in this for a full column rank is called the pseudo inverse. The right inverse becomes a pseudo inverse for a full row rank matrix. For a matrix which is neither full column rank nor full row rank, that is if the matrix turns out to be strictly less than number of rows, and number of columns, then you have something called pseudo inverse, for which the expression is different, which it's little difficult and little very advanced. Okay. Did that clarify the question?
Yes.
Okay, thanks. Okay, so yeah, good today that we spent quite a bit of time in revising the lectures of Professor. So now what I want to do is I want to get to, okay, we have already done the first question of tutorial. We'll then move on to the second question, okay, which is namely very important, and this is very fundamental that all of us should know when we are studying eigenvectors and eigenvalues. Okay. So the last time we stopped with basically computing the eigenvectors and eigenvalues, and we stopped means specifically with computing the eigenvector of an identity matrix. And then we showed that any non-zero vector is an eigenvector for an identity matrix. Okay, that's where we stopped last time. Now this time we are going to delve some very important properties of eigenvalues and eigenvectors, and then we'll go ahead. Okay. So let P be a polynomial, Let like P of X or P of lambda, whatever it is. Okay, be a polynomial. If lambda is an eigenvalue of A in C to the n cross n. That is, if I say that lambda is eigenvalue of an n by n square matrix. Okay, and X is a corresponding eigenvector. Then show that P of lambda is an eval or the eigenvalue of P of A, and X is an eigenvector of P of A associated with eval P of lambda. Okay, so let me first explain the question, what I'm trying to ask. So let's say there's a matrix A and its eigenpair is lambda comma x. That is Ax equal to lambda x. Okay, so lambda is eigenvalue of the matrix A and x is the eigenvector of the matrix A corresponding to the eigenvalue lambda. Now I do let's say P of x is equal to x square, or maybe x cube minus x square. Okay, it's a polynomial, right, in x. Now what I'm asking you to show is, show that P of lambda is an eigenvalue of P of A. That is, if I compute a cube minus a square, that is, evaluate the polynomial when x is equal to the matrix itself. If I compute a cube minus a square, then I'm asking you, so this is a resultant matrix, let's say B, it's also a matrix, then I'm asking you to show that for the matrix B, the eigenvalues are lambda cube minus lambda square comma x. This is what I'm asking you to show. That is, this is nothing but P of lambda, right? This is where lambda is the eigenvalue of A. So if I say P of A is equal to B, then this particular number, let's call it lambda dash. And lambda dash is nothing but P of lambda is equal to lambda cube minus lambda square is the eigenvalue of the matrix P, but the eigenvector remains unchanged. That is what I'm asking you to show. Okay, it's a very, very useful property. Once I show the solution for this question, I will give you some examples. I already gave an example, but we will see more concrete examples. Okay, solution. Okay. So remember, let me first recall what is a polynomial. Okay, P, I'm saying P is any polynomial. So I'm just writing polynomial in T. T is a scalar. t belongs to complex, which is scalar. Okay. P of t, what is the general equation for a polynomial? Ak power tk plus ak minus 1 in kth degree. Let me assume k degree polynomial. Okay. Ak minus 1 power tk minus 1 and so on till a1t plus a0. This is a scalar, correct? The sum, see, every term is a scalar here. So the entire sum is also scalar. Now what is P of A? Just replace T with the matrix A. So AK power A power K. This AK minus 1 power A power K minus 1. See, all these small AKs are all scalar numbers. Okay. And so until A1A plus A0. Can anyone tell me what I should do? I cannot just write A0 because these things are matrix. I cannot add a scalar with the matrix. So what should I write? Can anyone tell me?
A not
I.
I.
Exactly. Just I. So what is this sum? P of A is a matrix. This complete summation is a matrix. But here the complete summation was a scalar. Similarly, P of lambda. How is it defined? P of lambda? AK power lambda. AK times lambda power K. AK minus 1 power lambda K minus 1. And so on till A1 lambda plus A0. This is again, what is this? Sorry, can you repeat?
Scalar.
Yes, correct. Just scalar because eigenvalue is a scalar number. It's like just t equal to lambda. So now what we are asked to show, if ax equal to lambda x, that is if lambda is the eigenvalue of a with the corresponding eigenvector x, then we need to show that p of a times x is equal to p of lambda times x. This is what we need to show. Okay, that's what the question is. So let's see the solution. So what I will do, I'll take the LHS, take the left hand side. PA of x. So again confirming, PA is a matrix. Here you see PA is a matrix. What is the dimension of PA? And C to the n by n, because this is a power k is n by n matrix. This is also n by n. So I'm adding n by n matrices. It's again going to be an n cross n matrix. So PA is a n cross n matrix. X is a n cross 1 vector. Okay, so it's a totally n cross 1 vector. So PA is nothing but, let me write down what is PA of A. From here I can write down, right? AK minus 1, AK minus 1, so until A1A plus A naught I times X. I'm just expanding, I'm just writing down what is P of A. Now distribute X inside. Okay. What is this? AK into A power K times X plus AK minus 1 into A power K minus 1 X and so on till A1 AX plus A naught X. Now this has become this is the expansion. Now let's digress a bit. Very, very important. This is the key step. Let's consider A power, K or maybe A power mx. Okay. Just let me write down the steps. Please tell, excuse me, please carefully see through the proof and let me know if you have any doubt. I can write this A power times A power mx as A power m minus 1 times ax. But now what is ax? Lambda x. A power m minus 1 times lambda x. Lambda is a scalar, so like this is nothing but lambda into A power m minus 1x. Okay. Now again, so let me write down. So amx is equal to lambda into A power m minus 1 times x. Now do the same process again. I can write this as lambda into A power m minus 2 into ax. Correct? That's nothing but lambda into a power m minus 2 into lambda x, which is same as lambda square into a power m minus 2x. Correct? Is it clear? Is this step?
Yes, yes.
Yes.
Yeah. Now, similarly, I can again keep on doing. Similarly, this will become lambda cube into a power m minus 3 times x. It becomes lambda power 4 into a power m minus 4x. Is this clear? I can keep on doing the same procedure. Can anyone confirm if this is clear?
Yes, yes.
Yeah, correct. Then what happens? I can show that this becomes. I can in the end I will get lambda power
Lambda
m minus 1 into
into x.
ax. This is nothing but lambda power m into x. So what have I showed? I showed that a power mx is equal to lambda power mx m into x. Correct? This is what I have showed. What does it mean? This means that if lambda is the eigenvector of A, then lambda power m is the lambda is the eigenvalue of A, then lambda power m is the eigenvalue of A power m, and the eigenvector does not change. X is the eigenvector of A, and so is the eigenvector of A power m. So observation. If A has eigenpair lambda comma x, then A power m for any m. See, here I did not restrict what values of m. M was any number. Then A power m for any m has eigenpair. What is eigenpair?
Lambda to m and x.
Sorry, I missed you. Can you repeat again?
Lambda to power m and x.
Correct. Brilliant. Yes, true. Okay. So this is the crucial property I'm going to now use in this step. Okay, let me call this as step 2. Okay. Now let me rewrite step 2. What is step 2? P of A into x equal to ak power akx plus ak minus 1 a power k minus 1 x and so on till a1 ax plus a naught x. Therefore, by above observation, PA of x is equal to, can anyone, do you want to try? I can write ak power x as lambda power k into x. Similarly, I can write ak minus 1. This ak minus 1, a power k minus 1 x as lambda power k minus 1 x. Because that's what I proved in this.
Yes, sir.
And so on till ax is nothing but lambda x. And plus a naught x. Now take x outside. Ak lambda k plus ak minus 1 lambda power k minus 1. So on till a naught lambda, a1 lambda plus a naught times x. I just took the x common. Now what is this? P of lambda.
Lambda. Yes.
So what have I proved? PA of x is equal to P of lambda into,
X.
which is what I wanted to prove. See here. Okay.
Yes, sir.
This is a very, very important property of eigenvalues. So essentially, to summarize an example, let me write down some examples. If lambda x is eigenpair of A, implies lambda square comma x is e pair of A square. If same thing of A implies 1 by lambda comma x is eigenpair of, can anyone complete?
A inverse.
Exactly, A inverse. Okay, A inverse. If same thing, 2 lambda minus 5 comma x is an E pair of
2a minus 5.
2A minus
5.
5. Can I subtract
I,
this 5?
5i.
Exactly, 5. Similarly, if all this holds true, 1 by lambda plus 5i, where I is the imaginary number, that I, okay, is eigenpair of what?
A inverse plus 5.
5.
5i. Yeah.
That's all.
Yeah.
I.
Yes.
So this I is a square root of -1, that imaginary number I'm talking about, complex number.
Yes.
Okay. So this is, so what it says is you take any polynomial in the matrix A, then your corresponding eigenvalue will also have the same polynomial. You just have to compute the polynomial at the same eigenvalue. The resultant number is the eigenvalue of the polynomial name. That is what is the main
So can the
result.
right side is a PA if geometrically or what you say interpretation?
Sorry, I didn't hear you. What is the question?
Right side P lambda x is a polynomial, so it is a PCA expansion of what you say left side.
It's not PCA. Are you referring to principal component analysis?
Yes.
No. So P of A is just a polynomial. I'm not doing any kind of dimensionality projection or I'm not doing anything like that. I'm just saying that if you make a function of the matrix A, then how should the eigenvalue also be? I'm saying that if I have a matrix A and if I compute f of A, then the eigenvalue will also scale by the same function f of lambda. That's what I'm trying to say.
Yeah. Polynomial of A.
Yeah, that's where lambda is the eigenvalue of A. That's what I'm trying to say in this result.
No, now
Okay.
so suppose are you getting my words?
Yeah, but it's a bit patchy actually. It's
Getting
not very
yours?
clear.
No, but now if suppose we have a 2 lambda, suppose we take polynomial of order 2 and we have 2 lambda. So
Okay.
so can we say lambda 1 x and p of lambda 2 x is equal to right hand side ax is a principal component, what you say, bifurcation of A?
Well, it's not, because see, no, okay, maybe I should give an example. Then it's be clear. That's not what I'm talking. See, all I'm trying to say is, let's say A is a, okay, example. Again, I'm taking example 2104. Okay. Can you tell me the eigenvalues of the matrix? You can show that it is just equal to 2 and 4. Okay, because I think in one of the previous classes I told that
It's
for
upper
a,
triangular.
exactly for upper triangular matrix, the diagonal elements are the eigenvalues itself. Okay, so lambda equal to 2 and 4. Now, if I say a square, what is a square? 2014 square, right? Times 2014, which is nothing but 2 times 2 4 plus 0 is 4. 2 times 1 is 2 plus 4 6, and 0 plus 0 and 1 plus 0 16. Correct. You can show that a square is equal to this. What is the eigenvalue for this new a square? 4 and 16. You see 4 is nothing but square of 2, 16 is nothing but square of 4. Why is it square? Because I'm doing a square operation to a. I'm just saying that In principal component analysis, it's different in the sense you only want to retain the principal components. You want to ignore some of the eigenvalues. But that is not what I'm saying here. I'm saying how will all the eigenvalues differ with respect to the original matrix. Okay. Okay, I think that was an S, but I didn't hear you properly. Okay, let's move on because so let me now give you
Yes,
one
yes.
more question. Yeah, great. Let me give you one more question and then we can take break for some time. Okay, with that we will stop with properties of eigenvalues because whenever this necessary, I will delve on some more properties. So question 3. Some more properties of eigenvalues. Okay, this I won't show the solution, detailed solution of proofs, but you just know it. Okay, just know it. If ax equal to lambda x, that is, what does it mean? Lambda is eigenvalue and x is eigenvector for the matrix A. Then sigma of A is equal to sigma of A transpose. Okay, let me define what sigma of A is. Nothing but collection of all lambda such that Ax equal to lambda x. That is just a collection of all eigenvalues of the matrix A. That's all. What am I saying in this first result? I'm saying that the matrix A and the matrix A transpose will have the same eigenvalues. Okay, you can prove this by definition. What is the definition? Determinant of A transpose is same as determinant of A, right? And so is the determinant of A minus lambda I same as determinant of A minus lambda I whole transpose. And precisely all the lambdas that satisfy these equations equal to 0 are the eigenvalues. You can show that for both A and A transpose, the same lambda will satisfy the equation. That's why this particular result comes. I'm not writing down the proof in detail, but if you want, you can let me know. In the next class, I can write down the proofs in details. It's very simple proof. The next property, very interesting again, is suppose if A is a Rn by n, that is, it's a real matrix. All entries are made of real numbers. Okay. And lambda is an eigenvalue of the matrix. That is, it belongs to the set sigma of A. That is all set of all eigenvalues. Then lambda bar also belongs to sigma of A, where lambda bar is a complex conjugate. So first of all, what this result says is, for a real matrix, you can still have complex eigenvalues. Okay, that is no problem. But this result says that if the matrix is real, not only should that particular complex number be an eigenvalue, the complex conjugate of that complex number should also be an eigenvalue of the same matrix A. That is what this result is saying. So it's something like, why again it's a reminiscent. Why? That's because determinant of A minus lambda I is nothing but a polynomial. And we know that if the matrix is real, then all the coefficients of the polynomial are real. And that's it's a property of algebra, calculus, that the roots of a real polynomial occur in complex conjugate pairs. And roots of the polynomial that we are talking about are the eigenvalues. What is the polynomial? We are talking about determinant of A minus lambda I. And that has all real coefficients if A is a real matrix. That's why this particular result follows. Okay. A third property, sigma of A Hermitian is equal to sigma of A conjugate. That is, what I'm trying to say is, if you have a matrix A, let's say the eigenvalues of lambda, then for the matrix A Hermitian, the lambda conjugate will be the eigenvalue. Let me give an example. If maybe I'll explicit write down. If A has lambda as eval, then A Hermitian has lambda conjugate as eval. Okay. Next property. non-zero eigenvalues of AB and BA are the same. Counting multiplicities. What does it mean? Suppose if I have a matrix A and suppose if I have a matrix B, I take the product AB. Okay, I will have some, let's say C is equal to AB. Then I will have some eigenvalues for the matrix C. Okay, now suppose if I form the matrix B times A, let's call that matrix as D. So in general, we know that AB is not equal to BA. That is, matrix multiplication does not follow commutative property. That is in general known. Okay, so definitely see the matrix C, which is defined as AB, and the matrix D, which is defined as BA, are not the same. So their eigenvalues will also be. We may think that the eigenvalues will be different, but that's not the fact. Although the matrices C and D are different, their eigenvalues will be exactly be the same. And in fact, counting multiplicities. What do you mean by counting multiplicities? Maybe let me write an example. Example: if C is equal to AB, okay, then let eval of C is equal to 2, 2, 4. It's a maybe a C is a C in 3 by 3. Then D equal to BA. It's also let's say it could be not, it need not be 3 by 3. Maybe I will write non-zero. That's why I'm writing emphasizing the word non-zero very, very much. Zero eigenvalues, anyways they are zero, so no need to care. Let non-zero eigenvalues be 2, 2, 4. Then D equal to BA. Then we'll have non-zero even C equal to 2, 2, 4 only. It will not have any other number. What is counting multiplicities? Here the lambda equal to 2 occurs twice. Here also it will occur twice only. It will not be like 2, 4, 4. See, 2, 4, 4 and 2, 2, 4. The two, what are the distinct eigenvalues? 2 and 4. So it doesn't say just the numbers are same. It also says how many times they repeat will also be the same. So 2, 4, 4 cannot be the possibility. It should be 2, 2, 4 only. Okay, that is the meaning of counting multiplicities. 2, 4, 4, not possible. It should be 2, 2, 4 only. Okay. Maybe I will give two more properties. Then we will take a break, and then now I'll based on this fact I will give a good question. Fifth property. See, eigenvectors. I think this is a very standard question, standard result. Eigenvectors corresponding to distinct eigenvalues are linearly independent. What does it mean? Suppose lambda 1 is an eigenvalue of matrix A and it has a corresponding eigenvector x1. Lambda 2 has an eigenvalue, is an eigenvalue of A and it has a corresponding vector x2. Lambda 3 another eigenvalue of A and it has corresponding x3. If lambda 1 not equal to lambda 2 not equal to lambda 3, that is all three lambda eigenvalues are distinct, they are different. This implies x1, x2, x3 are linearly independent set. This is a result. It's a very, very standard result. Okay, it's a very standard result. So just know it. It's a proof is little laborious, but let's just know the result. The last result that I want to say is a very, very famous result. Determinant of a matrix A is given by product of eigenvalues. Okay. So what does it immediately tell you? If A is singular, okay, that is det of A, determinant of A is equal to 0. What does it mean? Can anyone comment on the eigenvalue nature?
At least one eigenvalue is 0.
Exactly. At least one eigenvalue should be 0. Only then the product will become 0. Okay. In fact, you should have asked me right here. I'm saying, okay, 1 by lambda is plus 5i. What is the guarantee that 1 by lambda even will be a finite number? The guarantee is given by A inverse. If A inverse exists, then 1 by lambda will not become a non-defined number, because lambda will not be 0 for any invertible matrix. On the other hand, see here, if determinant of A is product of eigenvalues, if determinant of A is non-zero, none of the eigenvalues can be 0. Everything should be non-zero number. So 1 by any non-zero number is always a proper number. Okay. So this particular fact does not contradict that also. 1 by lambda exists. It's a proper finite number because A inverse exists.
That is singular. Then how we can calculate the lambda?
Sorry, I didn't hear you properly. Can you repeat?
If a matrix is singular, how we can determine the lambda?
So if the matrix is singular, what do I know? I know some of the eigenvalues will be 0. But it's okay. You can always, if you expand the, see, determinant of A is equal to 0. It doesn't mean that determinant of A minus lambda, who told, I mean, this guy will not be 0, right? So I can equate to 0 and I can find all lambdas. So what, maybe I will take an example. Okay, I'll take an example. Okay, maybe what I will do is, I will write the next property and then I will take an example to find the eigenvalue of a singular matrix. No problem. Okay, now the last property is trace of matrix A is equal to sum of the singular values. What is trace? This is sum of singular eigenvalues. Sorry. What is trace? Trace means
Diagonal element.
Correct. It is a sum of all diagonal elements of matrix A. Sum of diagonal elements of matrix A is equal to sum of eigenvalues of matrix A. I mean, the proofs are very simple, but they require little more tools. So let me not do them, but just know the results. This is enough. Okay, so it's 7:24. What I would like to do is maybe take a break for about maybe till 7:29, and then we'll come back, and then we will solve some 2-3 problems involving some eigenvalues, and then we will see some 2 problems in least squares. The rest we will continue next week. Okay, so let's take break till 7:29 and be back. Okay, so welcome back. Okay, so there was an. Am I audible?
Yes, yes.
Yeah. Thanks. Example to find eigenvalues of singular matrix. Okay, so let me take an arbitrary singular matrix. What does it mean by singular matrix? It's sufficient to cook up an example where any two columns are dependent columns. So then it's not a full row, full rank matrix. So automatically it becomes a singular matrix. So example 1, 2, 1. Okay, 2, 4, 2, 1, 0, 0. See this? The second column is 2 times the first column. What does it mean? So A1, 2A1 minus A2 equal plus 0 A3, for example, equal to 0 vector. So I found two, my A2 means just 1 times A2. I found two numbers 2, minus 1 and 0 such that the linear combination is 0. Means what? These A1, A2, A3 are linearly dependent vectors. Therefore, A is a singular matrix. I hope you agreed with this point. Okay, so now let's try to find the eigenvalues of this such singular matrix. Not point. So what is the procedure? Det of A minus lambda I equal to 0. So let's just write that. Okay. 1 minus lambda into minus lambda into 4 minus lambda minus 2 into 4 minus 4 plus lambda plus 1 into 4. I'm sorry, this is incorrect, right? Minus 2 into minus 2 lambda plus 1 into 4 minus 4 plus lambda. Is this correct? I hope. Yeah, fine. Now let's expand it. 1 minus lambda into 4 minus lambda. There's a minus here. Plus 4 lambda and plus lambda equal to 0. This is nothing but lambda into 1 minus lambda into 4 minus lambda minus 5 lambda equals 0. I just took the minus common everywhere. So this becomes plus 5 lambda. There's a minus here. So take the minus that side. So it becomes minus 5 lambda. What does it become? Lambda into 1 minus lambda into 4 minus lambda minus 5 lambda equal to 0. Lambda into 4 minus lambda minus 4 lambda plus lambda square minus 5 lambda equal to 0. Lambda into, this is nothing but lambda square minus 9 lambda, minus 10 lambda plus 4 equal to 0. So what are the roots? Lambda equal to 0 and lambda square minus 10 lambda plus 4 equal to 0. Means here it's nothing but minus b, so plus 10, root of b square, which is 100, minus 4 in times 416 by 2. Okay, so means what are the eigenvalues? 0. So there's nothing but 84, right? 84 is like 4 times 21 So that is like 2 root 21. So 10 plus 2 root 21 by 2 and 10 minus 2 root 21 by 2. Sigma of A. So you see, did you understand the procedure? The procedure is same. There's nothing different. But all I'm trying to say is, since the matrix was singular, one of the eigenvalues is 0. Is it understood?
Yes.
Okay, great. So I had one more interesting problem, but I think I will defer that to next week. That is actually a very interesting problem. But I'll defer that to next week. I will remember that and defer to next week. So what I want to do is I want to do 2 more problems for today, related to the least squares, which I promised I will show today in the class. So the first thing is, we saw that A transpose A, the whole inverse, should be invertible, means A should be full column rank. There we had an argument that rank of A transpose A should be equal to rank of A. Why is that true? I'm gonna show the solution for that now. This is really the 5th question. Show that rank of A transpose A equal to rank of A, where A is a M by N matrix. Solution. Okay, so it's going to be a little non-trivial proof, in the sense, unless I tell that this is a solution, you will not be able to really see it. Okay, so the way I'm going to attack is basically by using the properties of null space of the matrix A. Let me, okay, this is rank, really the rank. Null space of the matrix A. So we will prove that the null space of matrix A transpose A equal to null space of A. Now let me just recollect the dimensions of the matrices. So A is C in M cross N, and A transpose A is C in N cross N. Okay. Now, is anyone able to guess why will proving null space of A transpose A is equal to null space of A help me in proving rank of A transpose A is equal to rank of A? Can anyone try to guess?
Ultimately, the rank is the minimum linearly independent, what you say, variables.
Columns are
Variables
rows.
yes. So if that is why the both A transpose A and A vector should have, A matrix should have the same linearly independent, what you say, variables.
I think you're right, going to the right point. So essentially, the way to formally prove is using the rank nullity theorem. If I show that null space of A transpose A is null space of A, what does it mean? It means, I'll tell you the hint. Hint is, it means dimension of null space of A transpose A equal dimensions of null space of A. This is something like what you're talking about, linearly dependent or independent variables. So they call something called free variables, right? This is what you're trying to refer to. That's what I'm saying. Just trying to refer by taking dimensions of these subspaces. But if you see, what is A transpose A? What is the number of columns in A transpose A? N. This is about N minus rank of A transpose A. What is dimension of this one by rank nullity theorem, right? Dimension of null space of A transpose A plus rank of A transpose A is equal to number of columns in A transpose A. Similarly, the dimension of null space of A by rank nullity theorem is, what is the number of columns in A? Again, N. N minus rank of A. Now, can you see where I'm coming from? If I'm able to show this is true, then this means rank of A transpose A is equal to rank of A. Is it okay?
Yes.
Yeah. So the key thing to do is prove that null space of A transpose A is equal to null space of A. If we are done with that, then we know how to complete the proof. Let's do that. So what is null space? Null space is essentially a set of all vectors such that A times X is equal to 0. It's a set of all vectors. Let me maybe write down for those of you who forgot. Null space of matrix A transpose A is nothing but set of all vectors X such that A transpose A X is equal to a 0 vector. Similarly, null space of the matrix A is a set of all vectors X such that AX equal to 0. So they both are two sets basically. It's a set of all vectors. So how can I prove one set is equal to the other set? How to do that? The correct thing to do is strategy. First, prove that null space of A transpose A is a subset of null space of A. And can anyone complete? What should I next do? Prove the other way around.
It is opposite null. Other way around, yes.
Yeah, you should prove this. If you prove both of them, then you're done. That this both of them together implies both these sets are identical. Null space of A is same as null space of A transpose A. They are identical. So we will just prove these two facts. Okay. So proof of 1. That is null space of A transpose A is a subset of null space of A. So what should I do? I should take any vector in element of the set null space of A transpose A and show that that also belongs to null space of A. Then this condition is satisfied. So let X be a vector in null space of. Maybe I will do the other way first. That is easy to see actually. Proof of 2. I'll just do this. This is very simple to see. Okay. Let X belong to null space of A. What does it mean? AX equal to 0. That's the definition of X belong to null space of A. Pre-multiply by A transpose on both sides. So you get A transpose AX equal to 0. What does it mean? X also belongs to null space of A transpose A because that's what it says. This equation says. So I first took an element of the null space of A and I show that that is also in the set null space of A transpose A. That means any element I take in null space of A is also a part of null space of A transpose A. What does it prove? It proves null space of A is a subset of null space of A transpose A. This is very easy. This way is very easy. Yeah, is there a question? Okay, I hope not. Now let's see the other way. That way is little tricky and very interesting also. It's a very beautiful way to prove. Proof of 1. That is null space of A transpose A is a subset of null space of A. Okay. So what should I do? I should take any one particular element of null space of A transpose A. Let a vector Y belong to null space of A transpose A. What does it mean? A transpose A Y equal to 0. The trick, I'm going to use a clever trick here. Pre-multiply the equation, the above equation. Yeah, is there a suggestion? Okay. By Y transpose. So what does it become? Y transpose A Y is 0. This is a 0 vector. This is a 0 scalar because it's a scalar number. You can show that. Okay. Now what is this? This is same as AY transpose AY equal to 0. Now can anyone tell me what is the next step?
AB whole transpose is B transpose A transpose.
Yeah, that's okay. That's what I wrote here. But can anyone tell me what is the next step? So what is X transpose X? Is the same as this?
Norm X square.
Exactly. So can I write this as AY norm square?
Yes.
Okay. Now what is the next step? If a norm of a vector is 0 or norm square of a vector is 0, then what does it tell about the vector?
Y is equal to 0 then?
Not Y. AY,
A is equal to 0
AY
then.
should be 0. Yeah, correct. AY itself should be 0 because AY is a vector and I'm saying that that vector's norm is going to 0. That means that is possible only if the vector itself is a 0 vector. That is a property of norm. A norm can be strictly positive for any vector and it is 0 only if the vector itself is 0. Correct? That means AY itself should be 0. Now, what does it mean? What does the AY equal to 0 mean?
It belongs to null space.
Y belongs to null space of A. So I took a vector in the null space of A transpose A and I landed up showing that that also belongs to null space of A. What does it imply? Is a subset of null space of A. Okay, null space of A transpose is a subset of null space of A. This is 2. So this is 1, that's 2. So from in 1 we show that null space of A is subset of null space of A transpose A, and in 2 we show that null space of A transpose A is a subset of null space of A. From 1 and 2, what do we conclude?
Dimension of both.
Not just dimensions, the two sets themselves are equal. Both the sets themselves are equal. Null space of A transpose A is same as null space of A. Since the set themselves are equal, then now the dimension of the spaces are also equal. Okay. Now by rank nullity theorem, N so A transpose A has, what is the number of columns in A transpose A? N. That's what I showed you. See, it has N. So N minus rank of A transpose A equal to N minus. Yeah, I think there is some noise in someone else. Maybe you can mute for some time. Okay. So what does it mean? Rank of A transpose A is equal to rank of A. Is it clear? Can anyone confirm if it's clear?
Yes.
Okay, great. So now I'm going to go to least square.
All
How
this
is
mathematics, sir, excuse me. Sir, all this mathematics is okay. There is no problem. But how, as the course is with respect to the engineering, so how this what you say engineering aspect is coming, that also like just like we said, we proved that curve fitting is a that estimate is so. Can you give example of this also, rank nullity what we have discussed?
Yeah, definitely. So you are actually setting the stage for my next question. Next question is, so why did I do this? I'm doing this to exactly tell what is the intuition behind least squares. What, under which conditions least square is applicable. So in fact, the next question I'm going to do, something called engineering application of doing a zero forcing beamforming, and how is least square the solution to mitigate interference. If I have two users, and they want to talk to the tower, how was the tower, the signal intended for one user does not go and interfere with the signal intended to other user. That is called least zero forcing beamforming. And with the next, I'm going to essentially do that. I mean, see, when you learn about a course, when you do, the course is called Applied Linear Algebra for Engineering, Signal Processing, Data Analytics, and Machine Learning. It's the important thing is you need to know how to apply the math tools, but you should also know when to apply the math tool, right? So that is also a part of the course. So that's why, so my tutorials in general are combination of both. I'll tell some math flavor where that will help you to understand when to apply a tool, and also solve some problems which will tell you which tools are relevant for which applications. Okay, so now I will do an engineering example. But before that, let me conclude why did I do this particular question. Because now let me go back to least squares. Okay, in least square solution, what was my solution? Exact was A transpose A the whole inverse A transpose Y. Okay, now we need A transpose A to be full rank equal to n, because A transpose A is a C to the n by n matrix. But rank of A transpose A is equal to rank of A. That's what we proved up above. Equal to n. But what is n for rank n? If that means rank of A should be n. But what is n for A? Number of columns in A. Therefore, A should be full column rank. Is it clear? Is it clear? Can anyone confirm?
Yes, sir.
Yeah, thanks. So now I'm going to do the last question for today, which is going to be one of the engineering applications, namely of zero forcing precoding. In MIMO signal processing. Okay. So exactly we have 10 minutes left, and I'll wind up this question in 10 minutes. Okay. So the problem is as follows. Consider a multiple antenna downlink system which comprises of NT transmit antenna and NT transmit antenna access point, means like the tower, for example. It's called the base station also in engineering terminology. And K single receive antenna users such that K is less than or equal to NT. Okay. Then zero forcing precoding eliminates inter-user interference. This is my claim, and I'm going to prove what does it mean. So let me discuss the system. What I'm in picture. Okay. So what I have is I have a base station, or I call it as a tower or access point. Everything is synonymous. Or tower, whatever. and it has NT antennas. Okay. I have several users. There are K users in the system, all of them with only one antenna. That's what I told, K single receive antenna users. Okay. This is UE. UE means user equipment or user itself. UE1, UE2, and so on till UE, maybe UE3, and so on till, let's say this is a UEK. There are K users. Okay. Now, for example, this is H11, H12, so on till H1 NT. 1 because first user. Similarly, HK1, maybe let me do next is 1, 2, and so on till NT. This is HK2, so on till HKNT. Okay, and likewise you do for all the channels are there for all the other users. Okay. Now what I'm saying is, what is inter-user interference? Let's say the tower at the same time it wants to send some symbol to UE1 and UE2. Now I need to ensure that the symbol that the tower sends to user 1 does not go and that is not received by user 2, because that's undecided, because user 2 wants only the data intended for that user, and user 1 should get the data only for that user. He or she should not get the data intended for other users in the system. So this is called interference. And if you do something called zero forcing precoding at the tower, that is before sending the data to all the users, you do some kind of operation, and that operation is called precoding. Okay. If you do some kind of operation such that this inter-user interference is cancelled or it is nullified, it's eliminated, then which kind of processing should you do at the base station? That is called zero forcing precoding. You need to do a zero forcing precoding in order to suppress the inter-user interference, and I'm going to show how this has relevance to the least squares and pseudo-inverse concepts. Okay, so what is the processing? So for that processing, let me write down the received equation. Okay. The received signal, let me consider a particular user, okay, of user small k. Okay. A particular user k is yk. See, it's a single antenna user, so it's a 1 cross 1 scalar equal to hk transpose x plus nk, where hk transpose is the channel between the base station or the access point and the kth user. So it's a 1 cross nt, and x is the transmitted vector from the tower, so it's an nt cross 1 vector. So it's an inner product between two vectors. This is 1 cross 1, and like that k is from all the users. Okay, all k users. It can be for any user. I'm considering one particular user small k, where how do I transmit x? X is equal to summation over I equal to 1 to capital K wi si, where si is belongs to C 1 cross 1 is the data symbol for user. Okay, such that the average power, for every data there's a power also, right? Average power of this is equal to the square, right? Expected value, the average is by expectation, power is by taking the square of the magnitude of the symbol, is equal to some pi, the power intended to the user, this particular user. Okay. And what is wi? Wi is a vector. Wi belongs to C to the nt cross 1. Maybe I'll write it down here. Wi belongs to C to the nt cross 1 is the weight vector for UEK, UEI data stream. That is The base station wants to send S1, S2, and so on till SK. Okay, these are different data for different users, but I want to send at the same time. So I do a summation, but I just don't do a summation. I multiply by a weight and then I do a summation. This weight vector, how do I choose W1, W2, and so on till W capital K? That will basically determine, that is the pre-processing. This is called pre-coding. I do some kind of weighting before transmitting into air. See, this is the X is transmitted into air, right? I do some kind of weighting of the data symbols before transmitting into air. This weighting is called pre-coding. Now, if the pre-coding has to be such that the inter-user interference is cancelled, then I will show that that pre-coded structure will turn out to be the least square estimate of the channel estimation. What we, the data detection we saw in the summary, and that has relevance to least squares. Let's see. I'll quickly wind up this in 5 minutes. Sorry for the delay. So let me write down what X is. Okay. So I can write X as. Okay. So I'm just writing down W1 S1 plus W2 S2 and so on till I'm just rewriting this particular above equation. WK SK. This I can write it as W1, W2, and so on till WK times S1 and so on till SK. So this is a matrix W times a vector S X. Okay, this is what? So let me recall. X is C NT cross 1, W is C NT cross K, and S is C and K cross 1. That is the data symbol for every all the K users there in the S vector. Now let me rewrite. Now let me collect all the received signals of all K users. So Y1 and so on till Y capital K equal to H1 transpose. See here, HK transpose times X. X does not have any K independence. X is just the vector that's transmitted from the base access point. H1 transpose, H2 transpose, and so on to HK transpose times X plus there's a noise vector. Let me call that as N vector. Okay. But what is this? Okay, let H be a matrix of H1, H2, and so on to HK. It is a matrix of CTC of NT cross K. Okay, because this is an NT cross 1 vector and collecting all of them is NT cross K. So essentially what is the, I can write above equation as Y equal to H transpose WS plus N. Okay, can anyone confirm if this is clear?
Yes.
Yeah, thanks. This is, so what is H? H transpose is K cross NT. W is NT cross K. And S is K cross 1. And N is K cross 1. So totally it is a K cross 1 vector. So all vectors are K cross 1 in nature. Okay. Now, what is the requirement? Now, what is inter-user interference nullification means? Let me just write down H transpose is nothing but H1 transpose, H2 transpose, and so on till HK transpose. For W is nothing but W1 and so on till WK times S vector plus N. Okay. Let me take at the first user. At the first user, UE or user, Y1 is a scalar equal to H1 transpose summation of I equal to 1 to capital K Wi Si plus N1. This is nothing but H1 transpose W1 S1 plus H2 transpose W2 S2, sorry, H1 only. So until H1 transpose WK SK plus N1. Now you see, For the first user, only S1 is desired. S2, S3, and so on till Sk are all undesired. Correct? So ideally, these guys should go to 0. Because that is called inter-user interference. For first user, only S1 is desired, not other Ss. Correct? So what does it mean? I need to define my W weights. Similarly, okay, let me complete it. Similarly, at UE2, Y2 equal to H2 transpose W1 S1 plus H2 transpose W2 S2 and so on till H2 transpose WK SK plus N2. For UE2, what are undesirable? Can anyone tell me?
Except S2, all other undesired.
Exactly. Should go to 0. And these guys should go to 0. Like that, you have constraints for all the users, K users. You need to design these Ws such that these off terms go to 0. This is called the pre-coding design. This is called the now. Let me give the solution directly. That is what do I want? I needed is requirement is Hi transpose Wj should go to 0 whenever I is not equal to j. You see clearly for decide H1 W1 here H2 W2 whenever there's a cross term product that is Hi times Wj wherever I and j are not equal, I want those terms to go to 0. Agreed?
Yes.
Yeah, correct. So then now let me go back to this equation y is equal to H transpose y H transpose W s plus n. Therefore, in other words, this matrix H transpose W, see this? See, this is my H transpose W, right? If I expand this, let me expand this. H1 trans, okay. We'll expand this. This is nothing but H1 transpose W1, H1 transpose W2, and so on till H1 transpose WK. So on till HK transpose W1, HK transpose W2, and so on till HK transpose WK. Okay, so if you see all the diagonal terms, we want them to be as it is. All off diagonal terms are such that they are of inner product of Hi and Wj where I not equal to j. So these guys should go to 0. We don't bother about what is the value of H1 transpose W1. We don't know. We don't want. I mean, we don't bother now. Our aim is only to cancel the inter-user interference. We are not bothered about how to get better quality of the desired signal. That is not the aim. So what does it mean? This H transpose W should become a diagonal matrix. That is the implication. Or it's better that H transpose W becomes identity. Or in other words, what is W? Can anyone tell me what W is now?
Inverse of HT.
But does the HT inverse exist? Is H transpose a square matrix?
No.
Yeah, what is H? H is, okay, here I defined, right? H is a NT cross K. And
Okay, so pseudo inverse.
Exactly. So it's a HT pseudo inverse. Okay. So what is it exactly? But this is H transpose, right? So this is nothing but you
It's
can
a kind
just
of it's a kind of
sorry?
Hermitian.
Sorry?
No, sorry.
No, not Hermitian. Okay, so this is nothing but pseudo inverse. Okay, now let me tell you. H transpose is in what? C to the K cross NT because H is NT cross K. Okay, K cross NT. But now you see the question I gave you one constraint. K should be less than or equal to NT. Okay, so that is NT should be greater than or equal to K. But here what do we have? NT should be greater than or equal to K. That means this is a this is a new thing. H transpose is a full row rank matrix. It's not a full column rank matrix. Okay, so the full column rank matrix that you studied till now was having, okay, for a full column rank, H pseudo inverse is given by H transpose H the whole inverse H transpose. For a full row rank, sorry, for a full row rank, H pseudo is given by can you just take the dual H times H transpose the whole inverse. I mean, just bring this H transpose here, and then whichever there's a transpose, remove the transpose. Wherever there's no transpose, bring the transpose. That's all. So this matrix, okay, W equal, okay, maybe I should write this. W equal to H times H transpose the whole inverse is the pseudo inverse, or maybe to be specific, it's called right inverse of H and the zero forcing pre-coding of the system. Okay, is it clear? Is there any doubt? You can ask me now. So I think I'm done with this today's class. So you can ask me if there are any doubts.
Sir, this is clear, but if you see the K, suppose users are suppose 1000 and on base station cannot have 1000 antennas. So the assumption what we said K is less than antenna is not correct practically, though the mathematically whatever you said is correct.
Okay, so that's a good point you raised. So for that, I will basically refer you to one particular concept called massive MIMO. Okay, so massive MIMO is basically a technology that people in wireless community use, wherein they want to deploy hundreds and thousands of antennas at the base station in order to serve a given set of users. In all these regimes, you see if you see this particular problem, I am saying simultaneously I'm serving all these K users. But in practice, that is not the case. In practice, at a given time instant, you may not serve all the users in the system. Maybe over a long time horizon, you may want to serve large number of systems. But at any given point in time, let's say now I fix a particular time slot, then it's not necessary that every user who is in that particular location will be talking over phone. There will be only subset of users who will be talking over phone. And if you can make out that historical information of whoever is going to, some average, if you're going to have an estimate of how many people are going to talk over phone, then accordingly you can design your base station antenna incorporating this massive MIMO technology. Is it okay? So remember this particular problem I told they are simultaneously served, means at the same time everyone is getting served.
Sir, yeah, you are true, but my just submission is like suppose in a densely populated area, base station has suppose 1000 antenna, but in that densely population area, users may have 10,000.
True, yeah. So then what people do is, then they will deploy multiple base stations, and they will reduce the coverage per base station, okay, such that the number of users within the coverage of a particular base station will be less than the number of antennas in the base station. You just put multiple base stations. That's all.
Okay, sir.
Yeah. Okay, so Okay, so let's stop for today. Maybe I'll stop recording now.